Yo! What's up, everyone? This is Bytor, according to the latest IEEE committee. We are back with a community favorite, the remastered series on advanced analog IC design. As a disclaimer, we would like to emphasize that we did not come up with this content nor are teaching it ourselves. All the rights are reserved to the owners of the lecture. One last thing before we jump into today's lecture. We just wanted to again thank everyone in the community, especially our patrons, for making this kind of content possible. You guys rock! Enough from me. Let's start with the next episode of the remastered series. Enjoy!
Alright, so for today what we're mostly going to be spending our time talking about is a little bit about just reviewing CMOS technology, but really actually most of the bulk of the lecture today and probably pushing into next time will be about passive devices. So, first of all, just, again, the point of talking about the technology here is really just to kind of get everybody onto the same page. And we'll talk some more later about kind of why talking about passives is an interesting thing to do. But just from 20,000 feet, in SPICE, it's really easy to just say, okay, R1 is between two nodes and has 10 k ohms or whatever the heck it is. But obviously in reality, things are not quite that simple. And in fact, as we'll see, a lot of times when you're dealing with analog design, it's actually the passives you spend more time worrying about than the active devices. So we'll get into that a little bit more. As I said, this time I won't spend a lot of time talking about the transistors themselves. We'll probably get into that in the next lecture. So here, this is, we're going to start out looking at just what the process looks like, again, just to make sure sort of everybody's on the same page. Now, in terms of what process we're going to be using in the class, we're going to be using this so-called 90 nanometer 1-poly 7-metal CMOS process. Now, the first thing I should say is this process is completely made up. So it only exists basically, in my own head and, I don't know, maybe in SPICE or whatever when you guys run it. Okay, so what that means is that it's basically bogus. So it's maybe based on things that are real, based on my experience, but, there's no real process out there that would actually match to exactly the models that I've given you. So in particular for the devices themselves, these are based on what's called a predictive technology model. But basically I just went and, plugged in some parameters here and there and got some curves back for the IV curves for the transistors and said, okay, yeah, that looks halfway reasonable. Now, the thing to keep in mind with that is that because this is not based on any real data, and all of the models, as we'll see probably next lecture, are kind of complicated, that means that there could be all kinds of stuff happening inside of that model that may not be real. So as an example, I don't think this is really going to happen, but you might even get things where, you draw some IV characteristic and it could do, let's say, that, right? Clearly bogus, but it's a model, okay? So the warning is when you're doing something with your circuit, if you're doing something and you're getting results that look like garbage to you, that probably means it's garbage. Not that, you don't understand, well, maybe you don't understand what's going on, but most likely it's garbage because if it's just too good to be true, it's probably too good to be true. Okay? Bottom line, don't just run SPICE and trust what it says. Actually think about what you're doing. Okay? So, in terms of just what is this thing going to be, as I mentioned, it's a 90 nanometer process. That means the minimum channel length, at least the one that you specify in the model, is 90 nanometers. I'm going to give you one level of polysilicon. In some processes, you get more than that. We'll talk about why in a second. There's 7 layers of interconnect. And maybe by today, if not tomorrow, and next time, we'll talk about actually why you'd care about that from the standpoint of doing analog design. All of those interconnects are going to be copper, just to reduce the resistivity. And just again, as sort of a default kind of thing, for this process, 1.2 volts is sort of like the nominal power supply. So you shouldn't really go beyond this, at least not without knowing what you're doing, because transistors start breaking down if you do that. Again, we'll talk about that more maybe in a lecture or so. But, from now on, if I say VDD, just, replace that with 1.2 volts in the back of your head. Okay, that's roughly what we're going to be talking about here. Now, this is not to say that, this is the latest and greatest process. In fact, this process is people were probably doing sort of state-of-the-art stuff in this maybe 6 years ago, maybe even a little bit more than that. So these days, if you were going to go out and do a design in like the latest and greatest technology, you'd probably be working in like 32, 45, maybe even 22 nanometers. But actually in analog, there's this long sort of tradition, I guess I'll call it, of trying to resist going into these technologies. Okay, so in fact, even if you go to like ISSCC today, you'll still see people publishing papers in like half micron technologies. So there's certain applications where that actually makes a lot of sense. But actually last year I decided that, I was just being too nice to you guys. So, I dragged you into the latest and greatest, well, not latest and greatest, but something sort of close to or closer to what you might actually see if you went out and worked in kind of a big analog mixed signal company. Okay. So again, not exactly real, but closer to real in any case. So again, what might sort of pop up in other places is particularly shorter channel lengths and perhaps actually lower voltages. A lot of analog mixed signal stuff, particularly for very specialized applications, let's say like RF power amplifiers, that might actually be done in like a bipolar or even silicon germanium heterojunction bipolar technology. That's certainly something you might see. And if you're really lucky or unlucky, depending upon who you talk to, you might even end up working with so-called SOI transistors. This is silicon on insulator, where there isn't even actually a substrate exactly there, and you get all kinds of weird, bizarre phenomenon happening. If we have some time at the end of the class, I may sort of talk a little bit about that, just in case people are curious. The other thing I should mention is, particularly in the analog mixed signal space, it used to be quite popular for people to sort of add extra stuff to the process to make your life a little bit easier. And so this is sort of, so-called adding basically analog mixed signal features, quote unquote. And those features actually, as we'll see, a lot of them end up having to do with the passive devices. So one of them is the so-called Silicide block. And as we'll see, that's to enable you to actually build reasonably large resistors without taking tons of silicon area in the process of doing that. Okay? Another sort of common extra device or extra thing you can get is high voltage devices. A lot of times these days, these are just used for the IOs in and out of the chip. But again, in analog mixed signal, sometimes that's actually sort of a useful thing to have because you want to be able to handle higher voltages. Another one that actually would be really nice if it was trustworthy, and I'll explain what I mean by that in a second, is, a lot of times in analog mixed signal, the biggest complaint people have about these modern technologies is that the supply voltage is just too low. Okay? And oftentimes you just basically run out of headroom to actually fit things inside of that supply voltage. So in some circuits, actually just the threshold voltage that you use on the device is kind of totally wasted, right? Because in analog, I'm trying to burn current through that thing the entire time, right? So I'm always trying to put some static bias on there. So sometimes you will actually get an option to have these so-called low VTH devices. Or in fact, sometimes you can even get so-called zero VTH devices, where the threshold is kind of set to 0 or maybe even negative. So that even if you put a very small voltage across the gate to source, the device will sort of conduct some reasonable amount of current. So again, potentially sort of useful in the analog space. Unfortunately, I would not recommend you use them too often. So anybody have a guess as to why I say that? Why is it that I say, there's something potentially nice there, but you may not want to play with it? Remember, somebody who developed these processes was probably thinking about not what you were doing. So what were they probably thinking about? What's kind of like the big money maker for doing advanced CMOS technologies? Digital circuits, right? So the guys who are in the fab, they're paying attention to the digital transistor. So if this low VTH device happens to just be there, they may not be paying too much attention to it. So from a practical standpoint, what oftentimes happens is even though you have this option, it's so poorly controlled that actually you don't know what you're really going to get. And so you're better off just sticking with something that you know what it is and designing around whatever issues that ends up causing, rather than having a bunch of just unknowns that potentially could screw you up and then make the thing not work. Okay? The other option, which again we'll talk a little bit more about later, is ways of basically getting more dense capacitors than you could otherwise get. So sometimes that's done with a couple of layers of poly with some insulation in between, or perhaps even different layers of metal. That's the so-called metal insulator metal, or MIM caps. Again, we'll talk a little bit more about that when we get into the sort of passive devices discussion. So before we sort of dive into really the core of the discussion today, again, I just wanted to sort of level set everybody to make sure everyone's just, kind of on the same page as what I mean by a CMOS process technology. Point here is we're talking about a Singlewell CMOS process. So there's a P substrate where you're going to form your NMOS transistors. There's an N well where you're going to form the PMOS transistors, but there's just that one P substrate for everybody. Okay? Now, there are a couple of things that I want to point out here, specifically from the context of analog, that even though you've probably seen this picture maybe even more than 5, let's say 10 times or something like that, you may not have thought about in the context of things that you really would care about over here. Okay? So here's just sort of the first kind of question for you. So let's say I go and I draw, in my circuit, one transistor over here. Let's say another transistor over here. Let's say that's some input voltage over there. And this is, let's say, some output voltage. And so if I was just type this into SPICE, would there be any, and just, let's do it the way I specifically, I'll give these things all labels. So I'll call these A, B, C. So these are all just the nodes that I've labeled there. Okay? So I go and I type this thing to SPICE and I try and simulate that circuit. So in SPICE, is there, assuming A, B, C, and VI and VO, those are all sort of independent of each other. Is there any somehow connection between those two transistors, or are they totally independent of each other? Again, in SPICE. Yeah, in SPICE, they're basically independent. Now, I was a little bit, fast and loose here, because there's still that body connection that you have to draw in SPICE. And so maybe, if I drew these to ground, then you'd say the only connection between them would be through that body, right? But if that's really quote-unquote ground, then that should be no connection, right? Okay, so in reality, what happens? There's a bunch of junk in between there, right? There's some parasitic bipolar junction transistors. In fact, even simpler than that, you'd like to say that when you tie that thing to ground, it's really ground. But of course it's not, right? There's some resistance there. There's actually, some diodes over here that have some capacitance associated with them, right? Let's say there's another transistor, there's some resistance over there. So in fact, actually, all those transistors are somehow coupled to each other through this big substrate network, okay? And again, the only reason I mention this is because a lot of times in analog, the thing that comes and bites you is the thing that's not in your model, right? And substrate, really classic thing that's just almost never in your model. In fact, I could almost argue that PMOS transistors are in some sense even worse from that standpoint, because every time you instantiate a PMOS transistor, there's usually some components there that sort of should be in the real, in real life exist, but SPICE never actually takes care of. So anybody have an idea which components I'm referring to or what they're related to? Specifically with PMOSs in like a single well process. What do I have to do to build a PMOS transistor? It's like the first thing I have to put. I have to put an N well. So, anybody know of another name for an N well sitting inside of a P substrate? It's a circuit element. It's a diode, right? So every time you put a PMOS, usually again in SPICE, you just do something like, okay, I've got my 4 terminals, right? But in fact, there's almost always some diode sitting there, basically from the body to the substrate, right? Actually, I guess I do that the wrong way, but you can figure that out, right? So basically, every time you instantiate a PMOS, there's actually extra stuff sitting there that completely never, SPICE is never going to handle. So again, point only being here, just pay attention, because sometimes that extra stuff actually is going to matter for the circuits that you're going to build. In particular, you can imagine, let's say I have some, digital circuit over here that's sitting right next to your analog circuit, right? That digital circuit, it's got really spiky current waveforms, right? Well, those little spiky current waveforms usually translate into some sort of variations on the voltage. And again, if you have some really sensitive analog circuit, that could basically screw up things that you care about, okay? So again, this is not actually a point we're going to spend a lot of time on for a while, but just keep in mind, it's usually the stuff that you didn't think about that can kind of come up and bite you at some point, okay? So just, now to give you sort of a little bit more specifics on the process that we're going to be working with, I'm just sort of giving you a few of the annotated dimensions here. So channel length, or rather, I should say, since we said the process technology is 90 nanometers, that usually means the minimum feature size you can draw is 90. For transistors, actually, even though the feature length is 90, the effective channel length typically is a little bit shorter than that. So in this process, it might actually be something more like 55 or 60 nanometers. But actually, that's turning out to be a sort of more interesting relationship these days, because now people are even talking about transistors where rather than the effective length being shorter, actually it's longer. So if you look at like a 22 nanometer process, people are talking about effective channel lengths of 23 or 24. Okay, if you're interested in why, come bug me, I'll explain it, but just keep in mind, process technology does not necessarily mean effective channel length of the device. Okay? Just a couple other sort of things that I wanted to point out here. These thicknesses that I annotated here are not sort of, obviously, again, this is just something I made up, but this is fairly common. So as an example of these sort of source drain regions and these contacts, typically they're about 50 nanometers or so thick in terms of the diffusion region there. Anybody have an idea why that might be something important that, again, you're going to care about in the context of an analog design? Why might it be important that it's 50 nanometers versus, let's say, I don't know, 10 microns or 500 microns or whatever? Series resistance, right? Anytime you got stuff that's thin, if you go for any appreciable distance, there's going to be resistance there, right? So just like you just said, every time you draw one of these transistors, actually there's some fairly substantial series resistance in those source drain regions. In fact, again, if you look at sort of scaling, that's one of the big deals in terms of things that people worry about how they're going to take care of that. Okay, so another thing to keep in mind. The other thing that's actually kind of interesting here, and again, I sort of annotated this, if you look at sort of a typical silicon chip, at least while it was on the original wafer, you've probably got a thickness of about 700 microns, maybe a millimeter or so. So notice, even though I could define these super thin features, like even this gate oxide of 1.4 nanometers, I've still got this pretty thick silicon wafer. Any idea why would I make it so darn thick? It's just easier to handle, right? Because you're processing that wafer, you're carrying it around, you're putting it in different machines. If you make it too thin, it might just snap in half, right? Now, by the way, if you actually looked inside of like your cell phone or something like that, if you kind of think about it, a millimeter is actually reasonably thick, right? Especially if I'm going to package that with something else and then stick it on a PCB, I may not actually want things quite that thick. So these days, it's actually quite common to take the silicon wafer and once it's been processed already, basically literally shave off the backside of it to try and knock this down to something smaller, let's say to 100 microns or so. Again, that's just so that you can sort of make the package thickness of the entire thing at the end of the day thin enough that it's usable in these really form factor constrained kind of applications. Okay? Again, that's just kind of the whirlwind overview of just what our technology looks like. Obviously, there was a bunch of layers that I didn't draw there, but that's just, again, to get everybody level set onto the same page. So now what I'd like to do is really dive in to talk more about passives themselves. Okay? But before we do that, I want to sort of ask the perhaps obvious question, but I'll make it a little bit more detailed of why the heck are we bothering to talk about passives? Just why might you care about it in analog circuits? And so the question I want to pose to you guys is, let's just pick your favorite analog circuit or maybe some simple analog circuit that you like to talk about. Let's draw that, and then maybe we'll pretty quickly see why passives are important. Regular. Okay, that's pretty reasonable. Okay, so bunch of different ways you could build that, but I'm probably going to have, let's say, something that looks, approximately speaking, like that, right? Okay, so now I'm going to have to build something that generates the reference for that thing, right? So I'm going to have maybe some load circuit over here, right? Okay, so now actually I didn't even really completely finish that drawing there. So let's ignore the fact that I need a reference circuit. We'll come back to that. That'll be another good example, but inside of this regulator thing here. So what am I kind of missing? What do you think you probably are going to need in order to actually build this and get it to work? A cap. Okay, where do you want to put cap? So you want to put a cap on this so-called V out, and presumably you want to put that to ground, right? Okay, why do you want that cap? So that's usually called a decoupling capacitor, right? You want to make sure that the output stays relatively constant. Right? So let's call that CD cap. Okay, I agree with you. You probably want that cap. Any other passive components you might want here?
You want resistors on the feedback loop?
Okay. Why do you want resistors in the feedback loop?
To control like the ratio, like the VDD to whatever output you're trying to get.
Okay. You could indeed do that. So you could do something like, I think what you're saying is this, right? So you're saying I'll have, let's say, an R1 and an R2 over here. Okay, actually, this is a great example. I like this one now. So you said I wanted this to basically control the ratio between the input and the output. So what you're kind of hinting at is that the gain is going to be set by something about those resistors. So in terms of, if I was building those resistors, what would you care about from the standpoint of the gain? What's setting the gain, and therefore what do you want to make sure works well? So it's the ratio of the resistors that sets the gain, right? That basically means you really want resistors that match, right? Okay, very good. That's one thing that we're going to spend a lot of time talking about. What else might you want from those resistors in this exact context here? You're choosing the values of these things. How would you choose, or roughly what would you want to set those values to? Large. Why do you want them large? The actual current I want is over here. Any current that I've got flowing over there is just wasted in some sense, right? So generally speaking, I want those resistors to actually be pretty large. Now, do I want to spend the entire area of my silicon chip to get, a giga-ohm resistor? Or even a mega-ohm or whatever? No, right? I want the actual chip. I want the load, right? My regulator is just something off on the side that's making the thing work. So not only do I want large R, but I want it to be compact, right? Okay, great. That's actually several of the things that we've talked about. So that's almost all of them. Just to sort of clean off this example here, any other passive components that you think might be important in this context here? By the way, this is usually the first thing they tell you to look at when you do feedback loops. You want to make sure the darn thing's stable, right? So usually, not always, but usually, you probably want to put your dominant pole kind of over there, right? Because especially if I just built this out of some, let's say, common source amplifier. So obviously this is not exactly it, but conceptually something that looks like that. It's a high impedance node, right? So I'm going to need some sort of compensation network. So what's like a common compensation network I might use? Okay, you said a Miller cap. I think you said an RC, right? So actually let's go and do some RC thing like that. Okay, so now again, for those capacitors, or actually for that capacitor, what might I care about? So I care about the ratio of that cap to the load. So again, I care about matching, right? I probably, again, may want something reasonably large in a small area. So again, I sort of care about, in some sense, density, right? There's one other thing here that I claim that is sort of interesting that we haven't exactly touched on yet. So in that compensation network, what's important about the resistor? So you want to make that R in the compensation, let's call it RC over here. You want to make that equal to roughly 1 over GM, right? Well, guess what? 1 over GM has to do with transistors. R has to do with physics, right? Kind of resistivity and materials and things like that. So if I was to really do this, in SPICE, I believe you that you could tweak that R to get it exactly to be 1 over GM. What would happen if you actually built this thing and let's say you got 100 of those chips back? What would happen? It's going to vary, right? So some of them are not really going to be 1 over GM. In fact, none of them are going to be exactly 1 over GM. They're going to vary. So the other point here is you care something about the absolute variation, right? So if you say that the resistor is a kilo ohm, you want to know, is it really a kilo ohm or how much does it vary around that? Okay? The point is, we've picked sort of one relatively simple circuit, although I guess, maybe some of you would argue with me since you spent a lot of time on it in 140, but relatively simple circuit. But already you can see there's this list of things we care about just from the passive devices, without even talking about the actives yet. Okay? So that's really why we're going to spend some time today just talking about, okay, how would you actually build these passives up? Now, because in some sense it's sort of the simplest, although it has its own issues, we'll start out in terms of our discussion about passives with resistors. We'll move on to talk a little about capacitors, and then we'll just really, really briefly sort of touch on inductors. So let's just get started with resistors. Now, with resistors, it's actually kind of one of these classic stories where, in one place you want it to be 0, and you can't make it 0. And in another place you want it to be big, but you can't make it big. So basically, no matter what you want, you don't get it, right? So in digital, they don't want resistance because it just slows you down, right? So in a digital process, they kind of do everything they can to make resistance go away. Well, we just said that in analog, sometimes we actually want big resistors. Well, so again, guess what? Life's no good because, whatever the digital guys did, they couldn't make it low enough for themselves, but it's certainly way too small for us, okay? And the way to see that is just to look at the so-called sheet resistance of some of the layers. Does everybody know what sheet resistance is? Or, raise your hand if you don't know what I mean by that. So, all sheet resistance means here is, if I look at any resistor, I could say that it's something like the resistance is rho times L over the cross-sectional area, right? Where what I mean by that is, if that's the direction of current flow, then that would be the length. Let's say that's the width, and this is the height, okay? Now, in IC processes, you usually don't get to control the height. So the way people like to quote resistance is to just sort of split this thing up and say that it's rho over H times L over W, okay? So what I mean by sheet resistance, which is often referred to as ohms per square, is just that quantity right there, okay? Because it just tells you if I was to draw a wire in my chip, I can calculate how much resistance or whatever it is, I can calculate how much resistance I get just by looking at the aspect ratio. In other words, what's the length divided by what's the width? So does that make sense to you guys? Or okay, perfect. So again, why is this important? Because if I want to make a big resistor, then what I really want is a fairly large resistance per square. Right? Because if I have a small resistance per square, that basically means I need to draw a really long, thin wire to get sufficient resistance. So just as an example, if I took, let's say, aluminum wire, by the way, copper is even worse from this standpoint. If I have like 60 milliohms per square, that means I need 20 squares just to get 1 ohm, right? So if I want like a kilo ohm, that means I need 20,000 squares. Big, not what you want, right? Similarly, actually, polysilicon and diffusion, these are silicided, by the way, so we'll come back to that. Those are maybe about 5 ohms per square, but that's still kind of low, right? So actually, the only one that, sort of looks halfway promising, again, from an analog standpoint, is the N-well. That one's at least got like a kilo ohm per square. Okay, so that's, that's not great, but that's kind of okay. So, by the way, why is the N-well usually sort of the highest resistance thing in there? Anybody have an idea? So it's lightly doped, and so that's why it ends up being relatively high resistivity. So at least from this first glance, it kind of seems like N-well is our best bet, right? In terms of trying to build resistors for our analog stuff. Okay, so let's try and build an N-well resistor. So I'm just going to draw the sort of classic side view here. So we've got our substrate. Okay, we're going to draw an N-well over here. And the way I'm going to build this resistor is I'm going to put one contact right there. So that's like an N+. Put another one over here, that's another N+. And then, that's where my voltage is going to be applied. So let's say this is V1 and V2. Okay, so I get some resistance there. What else do I get? So I'm going to have a diode, right? Because I've got a P substrate and an N-well, so guess what? I've got a diode there. Okay, so before I do anything else, what should I really make sure doesn't happen? I better make sure that darn thing doesn't get forward biased, right? So I better make sure this substrate over here, that's really ground. And that V1 and V2 over there, they better always be above ground. Because if they're not, then actually I'm just going to get a diode I won't even get the resistance I actually wanted, right? Okay, so yeah, I definitely need to reverse bias it. So if I reverse bias it, that also means I'm going to have some kind of depletion region here, right? So as you also mentioned, if I have that, that means I get some capacitance. Now, why is capacitance kind of bad in this context? Why do I not want capacitance? Let's maybe ask it a different way. So if I built a resistance, what kind of impedance was I trying to get? High or low? I want a high impedance, right? Well, if I have a capacitor, then at high frequencies, I'm not going to have high impedance anymore, right? So that's why sort of fundamentally, if I have a resistor and I get a capacitor, that's kind of bad news, right? Okay, that's all goodness. Now let's actually think a little bit more carefully. So what else is going to happen here? So I've got this N-well resistor. I've claimed it's a resistor. Okay, it's got a diode on it. That diode has some capacitance. Is there any other sort of things that, when you type R in SPICE, which is an ideal R, that are going to happen to this resistor that would not happen in SPICE? It's going to vary, right? It's going to vary not just based on that voltage, meaning the difference between something like V1 and V2 and the substrate. It's actually also going to vary based on just the voltage you put across it, right? Now, just to be clear, why is it that it varies? Why does the resistance vary? The depletion region is going to change, right? If I have more voltage across it, that depletion region is going to get bigger. And so the effective sort of thickness I have available to actually flow my current through is going to get smaller, right? And so in fact, that's actually why it depends on both of the voltages that I just mentioned, right? Because if V1 is higher than V2, and let me just draw this real quickly, and maybe I'll do it in a different color. Let's say that V1 is greater than V2. Well, I'm going to get something that sort of has this asymmetric profile, right? I'm going to have a bigger depletion on one side than I have on the other, right? Well, that's a different resistance, okay? And as you also hinted at, if I move this P substrate around, which is kind of implicitly over there, relative to V1 and V2, well, again, that's going to shift that whole profile around, okay? So bottom line, I can do it, but I'm going to have a lot of capacitance from that diode, and it's going to be sort of highly nonlinear, just because the depletion region is going to change fairly substantially as I move those biases around. Okay? So, doesn't sound too great. Well, the one good news is that it's fairly common these days that you get the so-called Silicide block option. So that just means that rather than them applying the silicide to whatever layers they usually do, which is usually polysilicon and the diffusions, you can just tell them, okay, don't put any silicide there. And if you do that, you'll get substantially higher resistance. Because again, the whole point of putting the silicide was just to drop the resistance. So if you do that, you can again get sort of kind of reasonable ohm per square types of numbers. So somewhere in the, let's say, 100 to maybe kind of couple hundred ohms per square. So not quite as good as that N-well, but still sort of reasonable. In fact, actually, sometimes they'll just give you poly resistors that have been specifically lightly doped to get you higher resistance, and then you can get sort of back up to this close to a kilo ohm per square kind of number. Okay? So that's kind of good news, so we can get kind of more reasonable things that maybe will have lower capacitance. But unfortunately, a lot of the issues that we talked about still aren't going to go away. Okay? So all of these things are still going to be voltage dependent. In other words, they're going to be somewhat nonlinear. And actually, I'll talk about this in a second. These two coefficients, they have to do with the voltage across the resistor versus the voltage relative to the substrate. And again, we'll sort of go through an example of why both of those matter one more time in a second. The other thing is, of course, none of these things are independent of temperature, right? So if you increase the temperature, then the resistance is going to change. In fact, it's actually kind of more interesting than that, because not only is it going to change, but you don't even necessarily know which direction it's going to change, because it actually depends on the material. So for most of them, as you kind of expect, you make it hotter, resistance goes up. Well, some of these, like the N plus poly and the N-well, their resistance actually goes down as you increase the temperature. Okay, it just has to do with ionization of carriers and things like that. Go bug one of the physics guys. I don't even know. Bottom line, that's what happens. Okay? So, just to kind of give you an idea of why that might matter, let's just go through sort of an example of what kind of these variations might do to you. Just, again, to give you a ballpark example of how big these things turn out to be. So, let's just take a look at a N plus diffusion resistor. Okay, and if I'm not mistaken, or actually let's call that an N plus well resistor. Okay? So, if we just look up on our table on the previous slide, we've got a TempCo of something like 1500 ppm per degree C. Okay, and I'm just looking at the absolute value here. Okay, so if that's how big my temperature coefficient is, by the way, ppm just stands for part per million. So that's just like, 1e minus 6, basically. Okay, and it's a relative variation. So it means something like, well, I don't want to do the math in my head, but something like 0.0015% per degree C. Okay? So what would be sort of a standard temperature range for you to deal with in ICs? So somebody said negative 40 to 80. That's kind of reasonable. Any other thoughts? Or yeah, 0 to 70. Okay, yeah, they're both about right. So 0 to 80, I put it as here. So minus 40, that's pretty darn cold. So if you're doing like military space stuff, that's, you probably have to go down that far, but usually you don't go quite that bad in sort of normal things. So for sort of in industry kinds of things, you probably do need to go below 0 because, you might just be happening to build a, I don't know, Wii that's going to be played in Alaska or something like that, right? So you usually go to like maybe minus 10 or so, but let's say 0 up to about 80 degrees also makes some sense. If you really push this will maybe go up to like 100 C, but not too much more beyond that because obviously things start getting, obviously very hot, but things start getting sort of soft and squishy in the chip when you do that. So don't want to go too much above that. Okay? So let's just make our life easy. Let's say it was 0 to 100 degrees C. Okay? Well, if I do that, then basically I have to multiply that 1500 ppm by 100, right? So if you do that, and assuming I did my math correctly, which I think I did, that basically translates into about a 15% variation in the resistance value, okay? And that's just from temperature. Pretty big, right? I mean, it's not horrible, but that's pretty big. So if you were really trying to set that dead on somewhere, guess what? Already kind of game is over, right? 15% is just going to be taken right off the bat just from you don't know exactly what temperature you're going to be at, okay? So that's one, again, sort of quote-unquote non-linearity or non-ideality you're going to have to deal with. The next one, which we actually kind of touched on quite a bit, so I probably won't spend too much time on it. I was going to draw a nice picture, but you guys kind of got it already, was this voltage dependence, or the so-called voltage coefficient. And so again, it's really quite easy to see for these so-called diffusion resistors. So here, this isn't an N-well resistor. It's actually that I put an N-well, and then I put the P diffusion inside of it, and then I'm using that as the resistance, okay? But the bottom line is, just like we had said before, if I move the voltage across that resistor, that's going to change the depletion region profile, right? And so because of that, that's going to change the resistance you get. So if you just take a look over here, if I sort of calculate the effective resistance, it's some nominal resistance, plus this temperature coefficient that we just talked about, that's this TC over here, plus this VC, again, that's really related to the voltage across the two terminals of the resistor. Now, as we had said a second ago, our life is not quite that simple because not only does the depletion region vary based on these two voltages, or rather really this voltage, because remember all voltages are relative, it also varies as you take V1 and V2 and move them relative to the body, okay? So that BC over here, that's the so-called body voltage coefficient. And the way that's calculated is just you take the so-called center point, or sometimes people will call that the common mode, and you just look at how does the center point move relative to the body voltage. That's what this BC over here is telling you about, okay? This makes sense to everybody? Clear where this kind of came from? Okay, so now, just to be sort of absolutely clear, so we've talked about this in diffusion resistors, clear sort of why that happens there. But if you kind of pay attention over here, I said that there was actually polysilicon resistors, and they have these coefficients over here too. Why does that happen? Why do polysilicon resistors also have these voltage dependencies and actually even substrate voltage dependence? Any thoughts? All right, let's actually draw a poly resistor, and maybe that'll help you guys. So, if I'm doing my standard process, let's say that this is going to be my polysilicon resistor. And I'm drawing the side view here. I'm going to have, let's say, some contact over there, some contact over here, right? Okay. What do I have underneath that polysilicon resistor? Well, I've got some oxide, right? And then I've got a substrate over here. Okay, so now, why is it that I claim this thing is still going to be voltage dependent? So there's a capacitance. What is that the fact that there's a capacitance there wouldn't exactly cause voltage dependence. There's just one last thing you have to remember. Polysilicon has a depletion layer, right? It's not a perfect conductor, so actually you get some depletion region sitting on that poly over there. So just like we had talked about for the diffusion resistor, same physical effect happens in the poly. Now, as you might expect, because it's poly and you generally dope it and all that, it's not as big of an effect, but it's still there. Okay? So, if you look at these coefficients, you can see they're quite a bit smaller than, let's say, that N well over there, but still non-negligible. Okay? Does this make sense to everybody? Clear now where that comes from? Okay. So, before we move on, let me sort of ask you a question. So, what if I really don't want this variation? What's some steps that I can take? And by the way, from the variation standpoint, I'm going to specifically care about the voltage variation right now. So what are some steps that I can take to try and sort of reduce the impact of those things? Anybody have any ideas? And by the way, I'm talking from a design standpoint now. You don't have to invent any new physics. If I know what that center point of V1 and V2 is supposed to be, I could just drive that VB to sit right at that center point. Right? Now, by the way, if you were to actually build this, any ideas sort of, how you might really do that?
I was thinking for a CMOS.
Okay.
Could you tie one of those ports to the VB, or does that not work with resistors?
Well, what do you mean tie one of the ports?
Because like with CMOS, you tie source to body, right?
Right.
So, similar here or not really?
Okay. So what you're saying is do something like that.
Kinda.
Right? Yeah. So you're saying something like, okay, take V1 and tie it to the body over here. You could do that. Now notice, all you've really done in some sense is translated it so that V2 is controlling everything. So you've kind of, you have now VC kind of plus VB over 2, right? So what you really want is somehow to figure out what really is that center point and somehow tie that to the body, right? So I guess in principle you could try and do what I just drew there. So you could try and like tap the resistor in the center and draw a wire over. In practice, what you usually will end up doing is you build some sort of like dummy circuit that just tells you where that center point is supposed to be and then makes that tie. Okay? But again, the point here is we're spending some time talking about this because A, not only so that you can calculate what the effect is, but B, you could actually go and do something in your design to try and fix it if you really have a problem. Okay? Any kind of questions on this, or? So, actually, on that note, we talked about one kind of trick we could play to try and compensate some of these issues out. Let's say, again, I really, really want to make sure that things have like zero sensitivity to either the voltage or the temperature. And let's actually use temperature now as an example. So let's say I'm doing some precision application, and I really, really want a resistor whose temperature coefficient was equal to 0. Anybody have any idea how you can do that? If I get one thing that has a positive temperature coefficient, and then I have a second thing that has a negative temperature coefficient, and I just put those two in series, I basically get something like 2 equations and 2 unknowns, right? So I figure out how big do I make that first R and that second R such that the total resistance is the resistance I want, but that the temperature coefficients of the two of them happen to just cancel each other out. right? So if I look at, maybe I'll do this in a different color just so it's clear. So let's say that's the R1, let's say that's the R2, so that the total resistance does something like that versus temperature, right? So it's exactly what you said, right? If I knew what those temperature coefficients were, in principle, I could build something that would actually cancel those two things out. And in fact, obviously, you could try and do the same thing with the voltage dependence as well, right? I've given you the design task of you need to build a very precise, thing. And so you want to try and sort of reduce the effects of these temperature coefficients. How many people would use this trick? Raise your hand. Good, you're at least brave. Who wouldn't use this trick? Okay, 90% of you have no opinion, so I'm going to force you. So I'll put it this way. Either you build this thing or you're fired. So, who would use this trick? Okay, and who would try and do something else? All right, so for those of you guys who would do something else, why would you want to do something else? Other than you'd be fired if you didn't try anything.
The temperature coefficient of resistors is probably pretty hard to control like that.
Ah, okay, you're going in the right direction. It actually turns out the temperature coefficient usually is not too bad, but you're actually going exactly in the right direction. So what else might be hard to control?
Do you know what temperature you're operating at?
So you're getting at, what if the temperature coefficients actually varied with temperature? And then you're absolutely right, things could kind of get messed up. But let's even ignore that. There's actually something even simpler that's going to come into the picture.
Resistance values?
Yeah.
Process variation.
There we go. Okay, so why am I particularly worried about that here? So you said basically those resistance values may be off. So what's the problem? Why am I particularly worried about that here?
Two different types of resistors.
There we go. There's two different types of resistors, right? So the one with the positive, this might be the N plus poly. This might be, actually, I think that's the P. Yeah, no, that's right. I think this is actually the P plus, and that's the N plus. Right? But it's two physically different things. Right? So when I do the doping of the P, that's completely separate from when I do the doping of the N. So if something is slightly different there, my whole compensation scheme basically breaks down. Right? So what I'm kind of getting at here is that when we look at basically the variations in the resistors, we kind of have to split things into a couple of categories, or we have to split them into different ways because, as we'll see in a second, and as we kind of hinted at already, if we can make it so that we're just matching two things that are otherwise the same, that's actually probably our best bet. Because anything we do other than that, we're introducing the opportunity to basically get screwed up. Okay? So again, if I just took some resistor and, I built it on a chip and I fabbed 100 or 1,000 or 10 million of these chips, and I looked at what's the value of those resistors, what you'd actually see is you'd get some kind of Gaussian distribution. Sometimes it's not even Gaussian, but you get some sort of distribution there. Okay? So you never get exactly the value you wanted, but you get some variations around that. Now, those variations, they can pop up from all kinds of sources. So the biggest ones tend to be just something like, I ran the silicon wafer today versus I ran the silicon wafer a week from today. The tools aren't exactly the same. I didn't exactly dope it with the same amount of doping. I didn't exactly have the right, thickness or the same thickness in both cases. I didn't exactly have the same width, right? So one big component of that variation is just going to be from, time A to time B that the parts were actually fabricated. Okay. The other type of variation you're going to get is actually what I would say is sort of an error. Okay, and what I mean by that is you intended for two things to be the same, but systematically you did something wrong that makes them different. Okay, and we'll actually take a look at some specific examples of that in a second. The last sort of piece of things is you did everything absolutely right. So from a design standpoint, you actually got everything to be exactly the same, but it's just when you manufacture things, you don't have perfect control, right? So there's always going to be some random variations there. Now, the good and the bad news, I guess, is that if you take care of that kind of stuff, you can make the random component really, really small. Okay, and in fact, that's even in some senses under your control. And we'll talk a lot more about that later on in the class, but basically the bottom line, you want to get rid of all of these other kinds of things because they're pretty darn big. Right? So I said here the absolute variations in resistance is something like 20+%. As we saw, temperature alone was like 15%. The process is probably another 20. The voltage coefficient could be another like 10-15%. So by the time you're all done, you can get some pretty substantial variations if what you cared about was the absolute value. So that's why, again, if you really look at analog circuits, and in particular why CMOS circuits have actually eventually been successful, it's because people figured out how to make sure that they made their circuits only depend on ratios of otherwise identical things. Okay? If you make it based on ratios, that you can do extremely well with CMOS. Okay, and I gave some numbers here, anywhere from like, let's say 0.1 to 1% matching. In fact, you can even do better than that. Okay, so just to give you some, idea, that's about 10, 12, 13 bits kind of resolution that you can get just based on doing that kind of matching. Okay? Again, your sort of goal in almost any circuit you're going to be building is to figure out how to make sure it really only depends on ratios of quantities and not on these absolute values. Because if you're stuck with absolute values, trust me, it's almost always the case the variation is way, way bigger than anything you want to deal with. Okay? So actually on that note, let's actually take a look at and see what can we do as designers once we've at least built the circuit that we know it depends on the ratio. How do we make sure we actually build those elements in a way that they really will only depend on ratios? In other words, that we didn't make any systematic mistakes. So, first thing you do if you were sort of to go and build a resistor, let's say that it was our regulator we were talking about before, and we wanted to set the gain to be like 2 or 3, depending upon what feedback network you're using. And so you wanted one thing to be R, and one thing to be 2R. Okay? So, most straightforward thing you'd think of to do is kind of what I drew up at the top over there. Right? So just say, okay, well, I have some R per square. So this will give me my R, and then I'll just double the number of squares, and that'll give me 2R. So, obviously, since I put the question mark, and since I'm asking the question, it's not really going to give you 2R. So, why not? What's wrong? The contact resistance is fixed, right? So if I actually look at this thing, what I really get is RC, meaning the contact resistance, plus the R of the physical resistor that I actually intended to build, plus another contact resistance here, right? Well, if I do exactly what's drawn on the thing on the bottom, I'll still get a contact resistance. Now maybe I really will get double the resistance in the center. But again, I've got another fixed contact resistance over here. And so clearly, if you work out the ratio of those two resistors, it is by no means 2. Now, you might be lucky. It might be the case that contact resistance is really small, and it doesn't matter. But, Murphy's Law being what it is, if you ever do this, I guarantee you the contact resistance will be dominant. Just by sheer luck. Okay? So, bottom line, don't do it. So you got to do something actually better. So the better thing you do is you do what's called a unit element. Okay? And to be clear, what I mean by unit element, and you should actually keep this in mind because this is really the number one most important rule in analog design, is the reason why you do these so-called unit elements is because you want everything to be exactly the same. Okay, and when I say exactly, I mean exactly. And no ifs, ands, or buts. And we'll see just how, detailed and annoying that exactly can actually get in 1 second. Okay? So in order to make things exactly the same, that basically means you have to take one thing and just keep repeating it. Right? And then the only way you get those ratios is by how you connect that one thing to other one things to basically build those ratios up. Okay? So best way to see that is with this specific example that I've given here. So here what I did is now, rather than just doubling the length, I said, okay, my unit element is this whole piece here, right? So it's the contacts plus the resistor. Now if I want double that resistance, I put 2 of these unit elements, and then in my nice low resistivity metal, I tie them together in series. Okay? I claim this is now a much, much better way of building that ratio of 2R versus 1R. Now, unfortunately, there's actually still a few things wrong with this particular layout. So, what do you guys think? What else is wrong with this? And again, when I say exact, I mean exact. So what else is wrong? The wire resistance is not exactly the same, although that's maybe not too bad because that's just sort of this short piece here. You could probably compensate for that, but you're right. So if I looked at this unit element, it has 1 resistance above it and 1 resistance below it. But if I look at this unit element, all it has is 1 resistance above it and nothing below it. In fact, this resistance up on the top, it's got 1 thing below it and nothing above it. So in fact, I could argue that none of these 3 is actually exactly the same. Now, by the way, anybody know sort of physically why this matters? Like, the problem that I think is really the biggest one is probably more like a 5, 10, maybe even 50% kind of problem. Or why might it matter that the environment is not the same? Anybody know? How do you actually build this? What's the process you use? Anybody know? Well, okay, in general, what processes do you use to build ICs? So you use lithography to sort of pattern something, and in particular for poly, you have to etch something away. Okay? Well, so it turns out the speed at which you etch things away depends upon the local density of poly that happens to be there in the first place. Okay, just basically if there's more material or less, you etch faster or slower. So in this particular case here, if you have something where at the end there's a bunch of stuff that's blank around it versus things that have a lot of poly nearby, the speed at which you do that etch actually changes. So what you'd really get, potentially at least in this particular example, is 2 thin lines that are etched a little bit more and 1 thicker line in the center. Okay? And again, it just has to do with it wasn't exactly the same. So even when you processed it, things ended up being a little bit different. Okay? This make sense to people or? Okay. I actually claim there's even one more. By the way, this, environment thing, that's the classic thing that most, guys who have seen analog or people who do analog will complain about immediately. There's actually one more thing that in fact might even be worse than that's wrong with this particular layout. And this one's much more subtle. So now let's see if anybody can pick it off. What else is wrong with this particular layout? If I look at the 2R, current flows in on that side and out on the bottom, right? Whereas in this bottom thing, current flows in over there, and of course, out over here. Well, guess what? For that poly resistor, having the current flow that way, meaning from right to left, versus from left to right, sorry, not the same resistance. So yeah, the way you solve this problem is whenever you build a unit element, don't have it flow in one direction. Have it flow in both, right? I'll draw a picture of that in 1 second. But basically, it's exactly like you said, because if every unit element has it flowing in both directions, no matter which way I place it and rotate it and, sort of potentially screw it up, I'll get the right answer, right? Because I'll always have it flowing in both directions. And so I won't ever get that mistake. You're absolutely right. Now, by the way, this is again sort of a processing thing. The reason why the direction may actually matter is because when they do the doping, that's generally at an angle. And it's at one unique angle for the entire chip. So things that go one way are not exactly the same as things that go the other way. Now, poly resistors, usually that's not too big of a deal. But by the way, all these tricks that we're talking about for layout to make sure that things really match, just as important for MOSFETs. And in fact, sometimes even more. Okay? So in MOSFETs in particular, directionality matters. I know, in fact, I say this all the time, that they're supposed to be symmetric devices. Turns out not exactly true. Okay, so if you really want to make sure that things match, make sure that you actually get the current flow direction right. So again, just to be sort of clear on what Will was saying, Will was basically saying that, okay, what I should really do to fix this problem is just rather than have my unit element be one of these things, actually have it be two, right? So now if I make this my unit element and build my 2R out of two of those things, then now everything will be fine, right? Because now in both of them, I'll have one thing with current flowing that way and the other thing with current flowing that way. Does this make sense to everybody? Or? Okay, so again, just to be clear, when you do real layouts in analog, you should do the same thing actually for MOSFETs as well. So anytime I build, MOSFETs that I want to match, I make sure there's always actually two physical transistors, maybe with a shared drain, but I make sure there's actually two physical transistors there, just so that I don't make this stupid mistake. Okay? Now, the other thing that, I think it was Will or somebody had touched on was, actually there's another sort of error embedded there, which was that, let's say there's just some gradient in the process. So let's say that, on one corner of the chip, let's say over here, I have a certain thickness of poly, and on another corner of the chip, I have a different thickness of poly. Okay? So if I'm going to be laying out resistors across that entire area of the chip, then I better be careful, because if I really want them to all match to each other, that's not going to happen simply because of that gradient in the process. Okay? So the way you fix this is with a so-called common centroid layout. And all that really happens here is you basically just arrange things so that the things that have relative value to each other are sort of spread over space equally. And to say that sort of a maybe slightly more technical way, if you looked at the so-called centroid of each resistor, it should always be in the same place. Right? So again, the best way to see this is usually with an example. So if this was my R1, what I'm going to do is split my 2R, which is, I'm going to call it here R2. I'm going to split that into two pieces. Okay? And those pieces are going to be placed symmetrically around the center point. Okay? So by placing them symmetrically around the center point, what you can see here is that if I have any spatial gradient in the xy direction, basically whatever error it causes on the top guy, it'll cause the negative error on the bottom guy. So that if I add the resistance of, this piece with that piece, it will indeed have double the resistance of what I wanted before. Okay? Of the center point, I should say. So again, this is so-called common centroid. This used to be really, really critical. So, back when people were first doing analog design, basically if you didn't do this, you were completely dead. These days, it's maybe not quite as important, just because for most things you work with, essentially there's so much stuff packed into a small area that if there was any really big gradient, the chip probably wouldn't have worked. Okay? So a lot of the layouts you'll see today won't exactly follow this layout style, because you can imagine if I have more than just one or two elements, pretty quickly it gets to be kind of a pain in the ass to really make this happen, right? Because you have to do all these weird interleavings and sharings and things like that. I mean, it's not too bad, but it just gets annoying, okay? So the good news is it's not like a horribly big problem these days, as long as the area you're recovering is not too big. But it's something you need to know about, because, every once in a while you'll get into that situation where it is indeed potentially a problem. So you need to know about it just to make sure you can actually check it. Now, there's one more thing that I did here in this layout to fix one of the previous problems. And it's actually sort of even annotated on the slide. So what's the other thing that I added to this layout here to try and fix it?
Dummies.
Yeah, dummies, right? So those dummies, which is just on these edges over here, the only purpose of putting those things there is just to make sure that the local environment for everything looks roughly the same. Okay? That's why that's there. Now, by the way, when you do this, and this is kind of a pet peeve of mine because I see people do it all the time, when you do these dummies, it's really common for people to realize that you need dummies in that axis. By the way, there's nothing magic here. If the two sides or the other axis are different, you'll still get an error, okay? So if you really want things to match, make sure that it's not only sort of matched in the dimension that people usually look at it in, but make sure the left and the right are also matched. And by the way, I mention this because I've seen this happen countless numbers of times. So people will do a layout for the first time, they put the thing down, and then there's some big blob of stuff over here and nothing over there, and they say, oh, look, I did this perfect matched layout. Okay, so you've been warned, don't do that. So the dominant effect tends to be the etch effect. But by the way, just to make sure these, let's say, 32 or 45 nanometer processes work, people are coming up with all kinds of funky stuff. Okay, so one example is now people are actually mechanically straining the transistors. So they put these capping layers that literally are either stretching or compressing the channel. Well, guess what? It's a mechanical thing. So if there happens to be some other capping layer not that far away on one side, and no capping layer on the other side, you get a different stress. And therefore, you get different characteristics. So bottom line, if you care about it, just make it the same. Because, if you make it the same, then just about no matter what they're doing, you should actually get the right answer. Right? Now, to be fair, you do want to know a little bit about what it is they really do, because obviously if you take this to the extreme, then all you can do in your entire chip is have this thing and then, dummies all around it. Right? And that's obviously not particularly useful. So kind of the spatial extent of things is important, but certainly in the local environment, meaning within, let's say, 10, 15 microns or so, you want to keep that basically the same. Turns out there's actually, particularly with resistors, life can be even more fun than this, because a lot of the materials that you like to use to build your resistors out of turn out to be somewhat thermoelectric, meaning that if the temperature is different, then it actually generates a slight change in the voltage. And so, if you want to avoid that, there's these sort of extra tricks you have to play. These things like basically these so-called serpentine resistors that are symmetric about 1 point. I'm not going to spend a lot of time talking about it. Bottom line, if you really have to do a really, really precise analog layout, get either this book or something like it and read through it and learn all of the nasty tricks you're going to have to play. Okay, because bottom line, if you really, really care about it, there's all kinds of ways you can screw up. The good news is, again, many people already screwed things up that way, so at least they can tell you, okay, don't repeat this particular screw up. Okay? The only other thing I'll mention here is obviously if you really want big values, generally speaking, you don't want things that, look like 10 millimeters by a couple microns, so you'll tend to do things like these serpentine types of layouts. Again, key is make sure it's a unit cell and make sure you get the current flow direction right. Okay? Okay, so just one last sort of brief thing on resistors. We said we can get maybe somewhere like 100 to maybe a kilo ohm per square. If you really want really, really big resistors, that obviously gets big quickly. Like let's say you wanted, I don't know, a gigaohm or something like that. That gets painful. So in some applications, you will actually end up just using a MOSFET as a resistor. And so the way you do that, unless, in case it's not obvious, is basically just put some relatively high VGS on the device so that you make sure it always operates in the linear region, right? If it's deeply in the linear region, then, the channel charge is relatively flat over there. And you can pretty quickly work out sort of what's the incremental or effective resistance that you get from that. Okay? So, I wrote out sort of a few of the equations over here. They're not sort of super critical. I think you guys can figure them out on your own pretty quickly. The only point there is that if you're going to do that, you just have to be a little bit careful to realize that even though you can get really, really big resistors, they basically suck in many different ways. So they suck, A, because the voltage coefficient is huge, right? Because as you change the voltage, you actually change the VGS. They suck also because the temperature coefficient is huge, because the threshold changes and the mobility changes and all kinds of other stuff changes. They suck even more because there's about 10 different physical parameters, if not even more, that can all change the resistance. So you may not really get exactly what you designed for. But sometimes you don't care, right? Sometimes you just want a big resistance, and if it's even varying by a factor of 10, as long as it's big enough, that's kind of okay, right? So anybody sort of, have an idea where might something like that be kind of okay to deal with? It's vary by factor of 10, but you just want it to be big. Where's a circuit that might help you with?
The noise in the bias circuit too.
Okay, yeah, bias circuits, right? So if I just have, let's say, I don't know, a band gap or just something that's generating some bias that I don't really care all that much about in terms of, maybe I want it to be relatively precise voltage, but I don't care all that much how much current's flowing through the thing, this might be okay, right? As long as I can tolerate the fact that the resistance varies, this might actually be okay. The other example that you also gave was, let's say like in a filter, right? So let's say I just want to make sure something is kind of filtered enough. So I don't care if it's filtered even more, I just want to make sure it's kind of slow enough. Well, again, you can use these sort of MOSFET types of resistors for those applications. So again, anywhere where just you need something really big, but not that critical exactly what the value is really going to turn out to be. And there's a couple of examples here of sort of things that people have done that made use of these MOS resistors. Okay, so I think we're basically out of time for today. All right, great. So we'll pick back up next time with capacitors. So see you guys.